All right, so a linear transformation is a kind of function. We use the word transformation instead of linear function because, well, we think of this as sort of a more dynamic process. So you know linear functions, right? From calculus. And that kind of linear function takes a number as input and gives a number as output. When we talk about linear transformations, the convention is, when we use that word transformations, that it's just putting us in the context of linear algebra. So when we say a transformation, we usually just mean that we're talking about a function on vectors. And instead of always thinking of it as an input-output kind of situation, we can think of it as, kind of a more dynamic thing, right? Like using the word transformation makes us think of something changing, right? It's not an input-output word. It's a transforming one thing into a different version of itself or something. Now I sound really philosophical, but let's just move along. So in the context of linear algebra, the analog to this thing up here might be something, well, like this. And this isn't what we call a linear transformation in linear algebra. And that's because this thing is not zero. So if B is not the zero vector, then T is what we would call an affine transformation. And when it is zero, that's when we have something called a linear transformation. So the actual definition says this. So if we have a function T that maps one Euclidean space to another Euclidean space, and they don't have to be the same dimension, that transformation is a linear transformation if a couple of things are true. A brief way of putting this would be to say that the transformation of the sum is the sum of the transformation. Right, so that is called the additivity condition. The second condition says that if we take the image of a scalar times a vector, we'll get the same thing as if we take the that scalar and multiply the image of the vector by that same scalar. So let's look at a couple of examples, I think. Now we've seen things that look like AX before, and that's really another way of thinking about what linear transformations are. So we've looked at things that look like AX equals B all semester. But now instead of thinking of like solving 3x equals 5, right, and solving for x, now we're thinking of that left-hand side as being our function and asking what are the possible output values, and if we plug in a different vector, what is the vector that will get out and stuff. We're thinking of this as a function. And so we know, if we look at something like A times X, we know that it's really a list of the left-hand sides of some system of linear equations, right? So if we have, let's see, I'll just pick something pretty easy. So let's say T of X is 6, 0, 1, minus 2, 0, 0, 1, 2, 3. So this is an a times x type of function. And if I multiply this out, I know what it's going to look like. It's 6x1 plus x3 and minus 2x1 and x1 plus 2x2 plus 3x3. So this is our input vector. And we plug in those right numbers and we'll get this output vector. Right, so for instance, if I want to know the image of 0, 1, 0, I just plug in 0, 1, 0 into these x1, x2, x3 slots, and this is what I'll get. I'll get 0, x1 is 0, and here, let's see, I'll get 2, so 0, 0, 2. And I can draw a picture of this, but it's not going to look like the kind of picture of a function that we would draw on the Cartesian plane, because this is, I mean, even the input and output are already three-dimensional. So if I start by drawing my 0, 1, 0, and if I take the image of 0, 1, 0, it's 0, 0, 2. So this was the input vector, and this is the output vector. And maybe you can see why it's useful to think of this as a dynamic process, because we can't just plot this as a curve on the plane, right? These are three-dimensional vectors mapping to other three-dimensional vectors. And they can actually, you know, you can have these three-dimensional vectors be functions of time, and then we'd see like maybe a vector tracing out a path in three-dimensional space. There's all kinds of applications, especially in physics and dynamical systems, that really emphasize the fact that this is a, you know, this can represent a dynamic process. Okay, so this is a linear function, I'm sorry, a linear transformation, but there is also this question about how to check that T is a linear transformation. And the answer to that question is that you have to go and actually verify those conditions that are in the definition. Oh, here they are. Right. So these two conditions are the things that have to be true. So you'd say, okay, with this transformation, you would want to plug in a U vector, like a U1, U2, U3, and a V vector, V1, V2, V3, for each of these spots in the left-hand side. So you compute the sum and then follow this formula to get the transformation. And the same on the right-hand side. And then just check to see that they're the same. And I went through a couple of detailed examples of this in the video that I posted. So I think I'll not spend the time to do it now, but it's really just a bunch of plugging in sort of technical checking. So I'll refer you to that. Now, let me say this. So when we think of linear transformations in Euclidean space, and Euclidean space, I just mean like R2, R3, etc. We can characterize linear transformations as maps that map lines to lines. And in fact, they map parallel lines to parallel lines. And the lines through the origin map to lines through the origin. And a quick way of saying that is just to say that the origin stays fixed. And if you watch that 3 blue 1 brown video that I put in one of the first pages in the module, you'll see really beautiful visualizations of what all this stuff turns out to mean in terms of like what the maps look like, how the lines get mapped to lines, and so on. But there are other kinds of vector spaces that are not just these simple kind of tuples of numbers, R2 and R3. And one really, really nice one is the vector space that is this set of polynomials of degree n. By the way, if you, I'm going to tell you that this is a vector space and kind of work through some of it, but if you want to see what it actually means to be a vector space in general, you can look at definition 12.1.2 for a definition of what a vector space is in general. And it's got an awful lot of conditions that you have to check, but we're not going to check those now. It just gets too technical. So here's the thing I'm talking about. So we'll take P sub n is the set of polynomials in X of degree n. So for example, P2 contains polynomials like 1 plus x plus 3x squared and negative 2x plus x squared. Right, these are all the polynomials of degree 2. And degenerate cases are included as well. So like 1 plus x, that's a polynomial of degree 2. Right? Basically anything that looks like a0 plus a1x plus a2x squared is going to be in P2. Now, I think that one of the best ways to kind of get your head around what this is and why it's a vector space is to just compare it to what we already know of as vector spaces. So I want to compare P2 to R3. So like, say something like P1 of x equals 3 plus 2x minus x squared. That is an element of P2, and so is, let's say, minus 3x plus 5x squared. Those are both elements of that polynomial set. And these vectors these are elements of R3. And do you see where I'm pulling the numbers from? I'm just trying to kind of draw a little bit of an analogy, right? These are the coefficients in order: constant term, first order term, second order term. Yeah. And same here, right? 0 is the constant term here, and then minus 3 and 5. Okay, so now let's just look at what happens, right? If we add P1 plus P2, what are we going to get? Well, we get 3 plus 2x minus x squared plus negative 3x plus 5x squared. And adding these up and simplifying, let's see, I'll get 3 plus, let's see, this is 2x minus 3x. So that's actually 3 minus x. And then I have x minus x squared plus 5x squared. So that's 4x squared. And if I, on the other hand, add up these two vectors, what's the sum of these two vectors? Well, I'll have 3. 2 plus minus 3 is minus 1. And negative 1 plus 5 is 4. And so I still get that same kind of correspondence. Do you see how that works? And in fact, you know, if you were going to do something like work with polynomials in some kind of way where you're encoding something and actually doing computations on a computer, this is exactly what you're going to have to do, right? How are you going to store a polynomial in memory? Well, you're going to store it as an array of coefficients. Okay, so addition seems to like kind of be preserved, right, in this parallel. Adding the coefficients is, whether they look like vectors or like polynomials, it doesn't matter. And the same is true for scalar multiplication. Like, what if we took a scalar, let's just say r, and compute r times this polynomial P1, well, if I'm going to compute that polynomial, I just distribute the r through the parentheses, right? So I'll get 3r plus 2rx minus rx squared. And if I were to compute the same deal over here, if I was going to compute r times 3, 2, minus 1, I would get 3r, 2r, and minus r. Again, exactly the same correspondence, right? Just as the coefficients of the different degree terms. Okay, so this actually, this kind of parallel between these two kind of worlds, right? The worlds of tuples of points and the world of polynomials of second degree is actually really pretty useful, especially when we can start talking about using linear transformations, because it turns out that differentiation is a linear transformation. So do you remember, calculus and taking derivatives of polynomials? I hope you remember how to do that. And you might remember that there are rules that the derivative of the sum is the sum of the derivatives, and that if you were taking the derivative of something, you could actually take any constant coefficient and pull it outside before you take the derivative, right? Like the derivative of 3 times the natural log of x is just 3 times 1 over x, yeah? So even just kind of casually thinking about it, you might remember that differentiation exactly satisfies these conditions. But what's really interesting is that we can now represent the derivative of a polynomial with an actual matrix. So let's just, maybe let's think of a sort of a generic polynomial that would be in this set P2. And the derivative, right, the derivative of that polynomial is a1 plus 2a2 times x. So I'm just taking the derivative with respect to x. And so that d by dx process is taking my vector a0, a1, a2 and transforming it into another matrix, or sorry, another vector, 0, oh, sorry, I keep doing this backwards, a1, 2a2, and 0, right? Because this is it's a1 plus 2a2 plus 0 times x squared. And so now I can actually write down a matrix. So I claim that this operation of differentiation is represented by the matrix that looks like this. So 0, 1, 0, 0, 0, 2, 0, 0, 0. All right, and let's check that out and see if you can see why. So let's take a polynomial f of x equal to minus 2 plus 3x minus 7x squared. We know the derivative of this, f prime of x, is 3 minus 14x. And playing along, I'm going to take the vector version of this, so minus 2, 3, and negative 7, and multiply it by that matrix that I wrote down earlier. And the result I'm going to get is, multiplying the first row by this, that 1 is going to just pick out that coefficient of what was the linear term. So I'm going to get, let's see, 3. And then I have 0 times minus 2, 0 times 3, and 2 times negative 7. That's negative 14. And then the last one's all zeros. It's just 0. And so that matrix gets me the derivative of a second degree polynomial that I'm storing as a vector. Okay, so differentiation is a linear operator. Another example of linear transformation that we can, or a linear operator that we can model like this in, as n-dimensional polynomials, is something like integration, right? As long as you agree that the constant of integration is some fixed number, like especially 0, right? We do have to make that kind of concession that our integration constant is going to be 0, but then you can actually model and accurately represent the integral as a matrix transformation. Okay, so this is kind of a lot, but I just wanted you to be aware of this space and some of the stuff that you can do with it. So when you do the reading about the nullity and range or column space or whatever they call it in our book, when you get to this example and the discussion here, you won't stumble too much. But it is covered as an example in. So I wrote this down. So the definition of a general vector space is 12.1.2. If you look at example 12.1.2, you'll see where they actually introduce this particular space. Okay, so the last thing I wanted to make sure to just discuss a little bit today is to talk about the transformations, linear transformations, and how they geometrically can transform the plane and why that's useful. So I don't know, like you can imagine if you wanted to draw a picture, like a cartoon of, say, a ball bouncing and hitting the ground, right? They kind of get deformed and then come back up. Or if you wanted to draw a picture of a ball rolling away, as things roll away, they get smaller, right? In terms of perspective. Or if you wanted to, let's say, make a animation where you have a smiley face do like a flip, right? Rotate around and get all the way back again. All of these things are things that we can do with matrices, linear transformations in the plane, so in two-dimensional space. So maybe let's just, let's start with squishing the ball. Imagine that the ball is actually, it's points, but it's, if we think of it as vectors, it's really like every point in this image is a dot that has a vector pointing to it. And when we get to the next frame of squashing our ball, those vectors are all just getting kind of squashed in the vertical direction. And it's a nice fact that you can find the matrix that represents a linear transformation by literally just figuring out what it does on the two standard basis vectors in R2. Let me write that down. The matrix for a linear transformation is completely determined by the action of the transformation on the basis vectors for the space. So for R2, that would be 1, 0, and 0, 1. For R3, you would have the three basis vectors like 1, 0, 0, 0, 1, 0, and 0, 0, 1, and so on. So in this case, like for squishing the ball, imagine that we perform that transformation on these two vectors, right? So we have a unit vector 0, 1, and another unit vector over here, 1, 0. And if we squash this, let's say by a factor of 2, what's the result going to look like? Well, if we're really just squashing vertically, then nothing at all is going to happen to that blue vector, right? That's still going to look like 1, 0. but the orange vector is going to change. Instead of going all the way up to 1, it's only going to go up to a half, right? We're squashing it down by a factor of 2. So that orange one gets turned into 0, 1/2. And now the way our transformation is determined is like this. So we just take the image of 1, 0. That's going to be our first column. So 1, 0 didn't change. And we'll take the image of 0, 1, and that will be our second column. It's like we're taking each column of the identity matrix and doing the transformation to it. Okay, and now you can, I mean, this is not a complicated matrix. This is a kind of matrix that we've seen many times before. It's an elementary matrix, right? It represents an elementary row operation, in particular, the one that multiplies the second row of a matrix or a vector by a half. So this is going to take this matrix. If I multiply it by something, it's gonna leave the first row alone and then take the second row and multiply it by a factor of 1/2. And if we've got that, then really what we're doing is squishing all the y components by a factor of 2. So if we take this matrix A and multiplied, like, I don't know, our smiley face by it, we would get a squished smiley face. It's gonna literally just bring down all those y coordinates by a factor of 2. All right, and so just in our last 10 minutes, let's look at rotation and come back to this idea that the matrix for a linear transformation is exactly determined by what it does on the basis vectors, the standard basis vectors. And let's just think about rotating our smiley face, right? So if we have our smiley face, maybe, let's put him out here. And we want to rotate him around. So he's at some angle, right? We've rotated some angle. And again, we're thinking of the smiley face as a bunch of vectors, right? Every point on here is a vector, or you can think of it as a point. And we're going to rotate all those vectors by some number of degrees, right? We're going to rotate each eyeball vector and the mouth vector and the chin and everything, right? Everything's going to get rotated by theta degrees. And what's the matrix that does that, so that we can have, stored in memory all these vectors that contain the coordinates of all the points that we're mapping, and we can just rotate them around the origin. So we're rotating around the origin here by theta degrees. We can get that by looking at where does the vector, what was I using for this, blue? Where does 1, 0 go if I rotate it by theta degrees? So I'm going to rotate by theta, radians or degrees or whatever, and I'm going to get another vector, and now I need to know what its coordinates are. And so if I rotate 1, 0 by theta degrees, what do I get? This length, both of those things have length 1, so that means that they're points on the unit circle, right? They're pointing at points on the unit circle. So whatever this theta is, I know that the x-coordinate of that point is cosine theta, and the y component is sine theta. All right, so that's one of them. That's going to be our first column in our rotation matrix. So r is going to be equal to cos theta sine theta. And now we have to figure out where, what the second column is going to be. So the second column, right, we're starting off with this vector 0, 1. And when we rotate that by theta degrees, we rotate this by theta degrees, we're going to get something else still on the unit circle. And in fact, if you just compare this, this slice of this pie to this slice of this pie, they are identical. So you can figure out that this is actually going to rotate to minus sine theta, and the x component, the y component is going to be the same as the x component of the other one, so that's going to be cosine theta. And that means our matrix is minus sine theta and cosine theta. And now if we take our smiley face and multiply the points in it by that rotation matrix, we're going to get a rotated smiley face. Oh, that looks like it got bigger too. Okay, so that again was a lot, but this is being recorded, so you can go back and look at it again if you want to. Let's see if we can just take a moment. We can, for example, write down the rotation matrix for, say, 90 degrees. And so what's going to happen if I plug in pi over 2? The cosine of pi over 2 is 0, and the sine is 1. So this will be 0, negative 1, 1, 0. All right, so if we use that matrix on a vector, we'll see that it'll rotate it by 90 degrees. So let's take this matrix 0, minus 1, 1, 0, and multiply it by, say, 3, 2. Well, if I multiply this by 3, 2, I'm going to get 0 times 3 plus minus 1 times 2, so that's negative 2. And then this will be 3. And if we look at the picture of this, starting at 3, 2, and then looking at the result vector, the result vector we get by that multiplication is minus 2, 3. And you can see that that's, you know, looks an awful lot like it's 90 degrees, even with my mediocre art skills. And that's exactly what happened. So we rotated counterclockwise by pi over 2 radians. And the one for 90 degrees is simple to compute, but you know, no matter what your theta is, that matrix works. Cosine minus sine and sine cosine. Okay, so I will let you guys go now. Have a wonderful weekend.